Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone, welcome back to our Deep Learning course. Today, we're restarting Chapter 3, TensorFlow Implementation of Neural Networks 3, and our whole focus is Part 3.4, using TensorFlow to implement logistic regression models. Let us learn how to use logistic regression and its multi-class version, softmax regression, for classification tasks. We'll use a super classic case handwriting, digit recognition. Part 3.4, TensorFlow Implementation of Logistic Regression Mode. First, let us get to know logistic regression. It is mainly used for binary classification, like judging if a picture is a cat or not, or if an email is spam or not. The core of this model is we have input features like the pixel values of an image, which we call x, and a set of parameters called beta, which are weights for each feature. Logistic regression takes these features, combines them with weights, and then converts the result into a probability between 0 and 1. This probability tells us how likely the sample is to belong to one of the two classes. But what if we have more than two classes, like distinguishing 10 digits 0 to 9? That's where softmax regression comes in. It's an extension of logistic regression for multi-classification. Here's how it works. The model first calculates a value for each class, like how matched the sample is to digit 0, digit 1, etc. Then it uses a method to turn these values into probabilities, so each class gets a probability, and all these probabilities add up to 1. For example, if the model thinks a digit is 8, with 95% probability, the other 9 digits will share the remaining 5% probability. Our case uses the MNIST dataset. It has a famous dataset maintained by the U.S. National Institute of Standards and Technology NIST. Let us break down what's in it. Training set, 250 different handwritten digits, half from high school students and half from Census Bureau staff. Test set, the same number of handwritten digits as the training set. Our task, teach the model to tell the difference between digits 0 to 9. We'll follow 8 clear steps to build the model listed on the slide. Import data, prepare data, show handwritten digits, create one-hot labels, build the model, compile the model, train the model, visualize the learned parameters. Let us go step by step. First step, import the MNIST dataset. TensorFlow has a built-in function to do this easily. Here's the code. The one-hot equals false part means the labels, which digit each image is, are stored as integers, like a picture of digit 5, has a label of 5. We'll convert these labels to a different format later, but for now, this is how we load the data. Next, we need to split the loaded data into training and test sets. Training data, x0, y0, this is what the model learns from. x0 is the image features. Each image is turned into a long list of numbers, and y0 is the corresponding digit labels. Test data, x1, y1. This is to check if the model works on unseen data. We don't let the model see this during training, so it's a fair test of how well it generalizes. This step makes sure the data is in the right format for the model to use. To make sure our data is correct, let us visualize some handwritten digits. We use Matplotlib to draw a 2-row, 5-column figure so we can show digits 0 to 91 per subplot. Create the figure and axes. Fig x equals plt subplots 2, 5. Then flatten the axes to make looping easier. For each digit 0 to 9, find the first sample of that digit in the training set. Turn the long list of features back into a 28 multiplied by 28 image. Since MNIST images are 28 pixels wide and tall, and display it with AXI. Show M. The slide shows these raw digits. You can see what the model will be learning to recognize. For multi-classification with softmax, we need to convert the integer labels, like 5, into 1 hot labels. What S1 hot? It S a vector with 10 positions, 1 for each digit, 0 to 9, only the position corresponding to the true digit is 1, and all others are 0. For example, digit 1 becomes 0 1 0 0 0 0 0 0. We use chars built-in function to do this. The slide shows a sample of YY1. You can see those 1s and 0s which match the softmax model S output format probabilities for each class. Now let us build the model using Keras. It's simple and straightforward. Input layer. The input is a 784-dimensional vector because 28 multiplied by 28 pixels equals 784 pixels total, so we set input shape equals 784. Fully connected layer, we add a layer with 10 units, 1 for each digit, 0 to 9. This layer combines the input features with weights. Softmax activation layer. This layer takes the output of the fully connected layer and turns it into probabilities, so all 10 probabilities add up to 1. The code is short. Before training, we need to compile the model. This means setting up the tools the model will use to learn. Optimizer, we use Adam, a common and efficient optimizer, with a learning rate of 0.01. This controls how big each step the model takes to improve is. Loss function, we use categorical cross-entropy. It's perfect for multi-class tasks with one-hot labels. It measures how far the Model S predicted probabilities are from the true labels, like if the model says a digit is 3 with 10% probability, but it's actually 5, this function will calculate that error. Metrics, we track accuracy. This tells us what percentage of images the model classifies correctly. Now it's time to train the model using the model fit function. Let us explain the key parameters. X0, YY0, the training data, and their one-hot labels. This is what the model learns from. Validation data equals X1, YY1. After each round of training, the model will test itself on the test set to show how well it generalizes. Batch size equals 1000. The model doesn't learn from all data at once. It splits the training data into batches of 1000 samples each, which makes training faster and more stable. Epochs equals 10. The model will go through the entire training set 10 times. Each time it learns a little better. The slide has a plot that shows how accuracy improves as training goes on. You'll see both training and validation accuracy go up, which means the model is learning well. After training, let us take a peek at what the model actually learned. We'll look at the weights from the fully connected layer. Get the weights. Weights equals model layers 1. Get underlying weights 0th. These weights are a 784 multiplied by 10 array, one weight vector for each digit. For each digit, 0 to 9, reshape its weight vector into a 28 multiplied by 28 image, just like we did with the raw digits. Use Matplotlib to display these weight images with a color map called seismic and label each one with the corresponding digit. What do these weight images show?
They're like the pattern the model learned for each digit.
For example, the weight image for digit 0 will have a bright outer circle because that's the shape of a 0. This helps us see that the model isn't just guessing. It's learning real features. Finally, let us go through the exercises to help you consolidate what we've learned. In real life, find 3 interesting image-based applications like face recognition or fruit sorting, and list their inputs, what data goes in, and outputs, what the app predicts. From the food image scoring case, in section 3.32, think of other features, like the number of colors in the food image, to add to the model. Build a new linear regression model, and compare how accurate it is with the original. Besides images, what other unstructured data have you seen? Unstructured data is data that isn't just numbers in a table like audio, music, speech, or text articles, messages. Give examples for the logistic regression model we built in section 3.4. Can you think of ways to improve the code? Like adjusting the learning rate or adding a regularization term to make it more accurate. Think of other multi-classification problems, like classifying different types of flowers or animals that can be done with logistic regression in TensorFlow.